In this video we are going to study about involutions and its application. So involutions are functions which is very useful in combinatorics and related problems. So basically an involution is a function defined on a non-empty set such that it is a bijection, and also I composition with I is a identity function. I dot I is Ix. Now, Ix means each element is maps to itself. That's Ix. So that's actually an involution. In other words, we can say that here the inverse of I. So because I is a bijection, we can talk about inverse, and this inverse would be I itself, and such bijections we call involutions. For example, if you take X as a non-empty set such that you having 1, 2, 3, and I define maps like this: 1 goes to 2, 2 goes to 1, and 3 goes to 3, right? So we need to understand I is a function from X to X. Okay, right. Here we can see I dot I equal to Ix. That's very easy to see, right? If I square of 1 would be I of 1. I of 1 is 2, and I of 2 is 1. So 1 goes to 1, right? So that's the idea. So after this we are going to prove a simple proposition from this. You can observe that I will give you some observation from this example. You can see X is 1, 2, 3, the set 1, 2, 3. That means X contains 3 elements, which is odd, right? And I defined a function like this: 1 goes to 2, 2 goes to 1, 3 goes to 3. So you can see that 3 goes to 3, right? So that is a fixed point. So any map, any element which maps to itself, we call a fixed point of that function. So in this case, I has a fixed point 3. So X has odd number of elements, right? 3. And whenever I make a definition of the map, I got a fixed point. But the theorem tells the proposition we are going to prove has this is not a coincidence. This is always it will always happen like this only. That means if you define a involution on a set with odd number of elements, right, then it always has a fixed point, right? So so you cannot avoid this fixed point. You will always have at least one fixed point, right? So here I have mentioned X is a fixed point of I if and only if I of X equal to X. So that's the idea. So we have to prove this, right? Yeah. So in order to prove this thing, we will be looking at something called directed graphs. That's very easy concept. Whenever you have 2 points, right, you can define 2 orientation, either from it's looking at a city, right? If you have town A, town B, if you want to go from town A to B, or you can go from town B to A, right? And these 2 orientation is possible between 2 towns or points, anything, right? Okay, let's talk about the proofs. So let's start with an involution on a non-empty set X, right? Since our set has need odd number of elements, so it will be definitely non-empty, right? Yeah. So at least one element is there. So let I be a involution on X, right? Now we can assume for generally, so since we taking sets with odd number of elements, let it be some 2n plus 1 for some n, at least one, right, and belongs to natural number. You just generally assume that is the cardinality. And also we have I square of x equal to x for every element of x. That's because it is an involution. From the definition it is true. Now let us define a directed graph in this fashion. This is not very necessary, but sometimes to understand it is understand the idea very clear. I think this is very useful. So let us define a directed graph out of our setting, right? So an edge x to y is present in the graph. So we define a graph like this, right? We can call that is maybe so here you have x and you have y here, right? So this is the arrow I am trying to use. If and only if ix equal to y. Suppose in an involution I of x equal to y, right? So you're taking x from x to y. So if something happens like this, x and y are elements of the x, non-empty set x, then if I of x equal to y, we define an arrow from x to y as like this. Now since I is a function, there is exactly one outgoing edge from all x in x. So basically if you define like a graph like this, there may be possibility that you will think of there may be many outgoing edges is possible, right? Because we are just telling it's a directed graph, but it's not possible. Why? It is because from a function, if you define a function on a set x, you can only there is only a unique image for every x. So because you cannot have many directed edges going from x. Okay, yeah. Similarly, we can see that exactly one incoming edge also. This is because it is a bijection. So it's a one-to-one and on-to. If suppose somebody is coming right here coming to y, then the problem is then it is not a bijection. From x to y there is a map, and if you from z to y is on a map, so it will, so two fellows sharing one element in the range, so that it cannot be a bijection. So because it's a bijection, you can't have an incoming edge. So basically there would be exactly one. Okay, exactly one is possible. Why? Because onto, right? Onto-ness telling that whenever you take an element from y, there definitely exists a pre-image. So there is exactly one element, one edge will be there, right? Also in involution, the case of involution, you can see that if I of x equal to y, then I of y must be x, because when you compose it with I itself, you should get back the x that we have started from. So I square of x equal to x, right? So that's very important. So if I of x equal to y, then I of y must be x. So this gives you a nice picture, a nice component of the graph, which is when x goes to y, then definitely another arrow is y goes to x, right? So n x goes to y, y goes to x. Now we are all set to prove our result. Okay, so let's take x belongs to x, right? And we will telling all the things from the beginning, right? I mean whatever I have said for the bijection, right? So x belongs to x, then there exists a y such that I of x equal to y, definitely, because it's a function, it should map to somebody. If y equal to x, then we are done, because if y equal to s, then it is a fixed point, I don't have to go back. So let's assume y not equal to x, right? If not, what happens? We get this condition, exactly one edge going from y and exactly one and also exactly one edge going from y, and it should go back to x, because of I square equal to identity. Because of that reason, we will get this component x goes to y and y goes to x for two different elements from x. Now we choose another element z, which is not these two fellows. I mean z is not equal to x and y, right? Yeah. Then z is not adjacent to x or y. Adjacent means, suppose I take z here, then by any means it is not connected. For example, it is connected by this, like this, suppose. Then it violates the idea that it has exactly one incoming edge. So it's not possible, right? Now suppose the arrow is like this, then what happens? Then it has two outgoing edges. That's also violates the idea that it has only one outgoing edge. So z cannot be connected to y or z in that manner. So they are like separated, they are completely, that component of the graph is completely disconnected from others fellow, right? So z is not adjacent to x or y by any edge, since I is a bijection, right? Since I is a bijection. Now if I of z is equal to z, then we are done, right? If you choose I of z equal to z, then we are done. Otherwise what happens? You get a w which are disconnected from x and y, right, but connected to z, and this thing will happen. So in that case we are picking, first we picked x and y different element and made a connection, and then we put aside, then we get z and w, we put aside, right? So this is the way it's going. So in this way we can exhaust the elements in x. But if you do that, you can only do it n times, because this is 2n plus 1, right? So pairwise, if you exhaust the elements in the x, what happens is 2n elements is out, then one fellow will be left, because it is 2n plus 1, right? So if you do like this, one fellow will left, right? Then let it be k, right? Let it be k. So what happens to k? K has also this property, one outgoing edge, one incoming edge, and the problem is this k is disconnected from all the other elements. So what happens? We will form a loop like this, k going to itself. Now what is the meaning of that? I of k equal to k. So whenever you construct such a bijection, you will be forced to have a loop in that graph, right, in whatever the manner you choose, right? If this is an odd case, so you get a fixed point. So if you start an involution, start making an involution from an odd number of elements, then you will definitely end up with at least one fixed point, right? So that's the theorem. So what we can say, another idea from this, a kind of corollary we can make. So as said, with the even cardinality, then it always possesses an involution having no fixed point. That means we can construct such a fixed point. So if x has a cardinality is even, then we can construct an involution which has no fixed points, right? That's the idea. And what are those things? So these are exactly we can connect this to a very nice set, because suppose you take x is equal to 1 2 3 4, this one. If you choose this set and you consider a partition, a 2-element partition of this set, right? So when I say, like, what do you mean by 2-element partition? Means partitions, right? It is subsets, and the union will be x and intersection is empty, right? So look at this. If you take union of 1 2 and 3 4, you will get the complete x. Also their intersection is empty. So this is one 2-element partition of that. You can make other also. If you replace 2 by 3, then you will get 1 3 and 2 4. That's also a partition. And from this you can define an involution. So how do we do that? So if I want to define an involution, whenever you get a partition, that's very easy, because you define like this: 1 goes to 2 and 2 goes to 1, right? Similarly 3 goes to 4 and 4 goes to 3. So this defines an involution, right? For example, if you want to find out I square of 4, this is I of 4, and I of 4 is 3, right? And I of 3 is 4. So it just fixes this. So this is an involution, right? So this is always possible when you take a 2-element partition of the set X, regardless of the cardinality. If it is even, or we can't, there will be possibility, right? So yeah, you will not get a 2-element partition for odd number of elements. That is another corollary. Maybe again we can try here. There is no 2-element partition. 2-element partition for X with odd cardinality, right? Because we cannot pair it like there will be some intersection, so you can't do that. So that's a corollary from this kind of idea, right? Because if you can do this, you will get an involution which has no fixed points. So that's not possible, right? That's I came up with while doing this, right? So now assume, so generally when you say suppose p equal to xy and x not equal to y, they are all belongs to x. That is a 2-element partition, right? What do you mean by that, right? And if we define ix equal to 1 and iy equal to x, so we get a involution, right? Yeah. So that's the idea. Okay. So applications to combinatorics, right? So how do you prove something using this and the kind of involutions? What are the use of this? So this is an application, a summation. This is a summation, right? So maybe you can write summation. So this is summation, and ck and choose k, right, times -1 raised to k equal to 0. That sum is 0. So going from 0 to n is at least 1, right? Yeah. Now how do you prove this? So the proof is based on involutions. So let's denote the square bracket of n is a set 1 to n, and that x is the power set of this. Okay, so power set of the box n. Now we want to define a function which is a sine function. So I want to define a sine function. So this sgn is basically going from n to not n, the power set, so x to plus or minus 1. So that is basically called sine function. Any function from non-empty set to plus or minus 1, we call it a sine function. Let it be like that. So the sine function we defined, the definition is very simple. It is -1 raised to cardinality of that subset. So let S be a subset of box n. So that would be an element of x, and the sine function we defined is -1 raised to cardinality of s. So definitely that will give you either plus or minus 1, depends upon the cardinality of s. coordinate of s is even, it will be 1, odd is it will be -1, right? Yeah. So suppose we know there are many subsets are available in box N. We choose a subset with cardinality k. So all the subset with cardinality k, the SGNS, the signature function or sign function, right? That can be written like this, -1 raised to k. So all those s's we have -1 raised to k. So how many element subsets are of cardinality k? That many fellows have the sign is -1 raised to k. So I can just write like that. So the number of subsets with the signature -1 raised to k, a sign -1 raised to k, is nck. So all those fellows, if you put into that, then you will get -1 raised to k. What is that? Whether it's odd or even. So we are going to make idea, because the summation s belongs to x sin s, right? SGN of s. That means if you are adding all these things, then it would be exactly look like this, because nck, you choose one element subset and then corresponding sign, how many signs will come? -1 raised to k, right? And you take a 2 element subset and C2 into -1 raised to 2, right? Like this. So the sum of all the signs will be also expressed like this. Summation k from 0 to n and ck -1 raised to k, right? So that's the idea. Now we are going to define an involution. So this equality, we need it. We need this idea. Okay. So now we define an involution I of s, right? Involution is defined from x to x, right? So the idea is simple. If a subset has a 1, then we avoid it. Okay. So then still you are getting a subset from x, the element of x, right? If an element has no, so this is if an element has 1, you avoid it. If element has no 1, you will the element 1 is not available, then you add it. So what is happening is, if the cardinality of s is changing, I mean the parity is changing. I mean suppose s has even, then I of s is odd. If s is odd, I of s is, because you are adding or subtracting the element 1. Okay. And also it's a bijection, there is no worry about that. That's very easy to prove, right? It is well defined, and you get it is a bijection, right? So the function is very simple. You take a subset of x, I mean you take a subset of box n or subset element of x. If there is 1, you avoid it. If there is no 1, you just add the element 1. Okay, right? Easily you can see that if you put 1, if s has 1, you take it, and again you put back, you will get the x. So it's an involution. I square s equal to s. I square s equal to s. Okay. Now we note one more idea. I told the sign is changing, right? So the SGN of I of s is now is an element of box n. So you can look at this. Now SGN of I of s is a minus of SGN of s, because they are different, right? Their parity is different. Because of that, you can easily verify this, right? So this is very important. The SGN of I of s can be equal to minus of SGN of s, because they are different in parity, right? Okay. Yeah. So I has no fixed points. That's very easy, right? So I has no fixed points, because every time when you put s, as Sgn of s is a negative of that. So so I has no fixed point. I'm not talking about Sgn. What is I? Whenever one exists, you are avoiding one. So or one is there, one is not there, we are adding. So definitely it has no fixed point. Okay. So I has no fixed point. So since I has no fixed points, I is an involution also. So this tells you that a kind of pairing can be possible, right? So how do we pair? We pair like this: S and I of s, right? So right, because it has no fixed point, we can always pair like that, a subset S with the I of s. So what I am going to do is, we will write this fellow, right? Summation S belongs to X sine of S. We will rewrite the sum such that maybe since X is a finite set, the subsets are also finite, so Si from 1 to n. So we like this: Sgn of Si plus Sgn of I of Si, because this pairing is possible because it has no fixed point, right? This kind of pairing is possible, and it is a bijection, so surely you can do that. And how much I will go, because when I write like this, definitely the half of index I need only, because I split this into two pairs. So definitely you only need cardinality of x over 2. I going from cardinality from 1 to x over 2, Sgn of Si plus Sgn of I of Si. That's easy because you split the sum. And what happens is, Sgn of Si plus, what is Sgn of I of Si? We already found that there is a negative of S. So it is Sgn of Si itself. So what happens? You get a finite sum of zero summons. So that means this is 0. And we already have observed an inequality, which is this fellow is exactly equal to this. That means it is 0, right? So here we successfully created an involution such that we can end up with a beautiful equality, right? So that's the use. So hope you understood the idea of involution and its use in problem, right? Okay, so let's wind up. Thank you.